All right. Hello, everybody. It's been a long time, and I'm glad to see we've got a fairly decent crowd that showed up for the webinar. Apologize that we've taken a decent chunk of time off here, but yeah, I'm Todd Alford. I think a lot of you guys know who I am, and common face for been around doing support for quite some time. I brought a new face with me and thought we'd do an interesting little webinar for you guys. We'll get in and kick off. Get kicked off. We both kind of did a project and went separate ways to see what was the same and what was different. A little bit later when we came back together. I'll let Amal introduce herself.
Hi everyone, this is Amal. I'm really a young CFD technical support specialist in Autodesk, and I'm right now located in Munich in Germany to support CFD products. And previously I worked on different interesting CFD projects related to automotive applications, and my love story with CFD started during my master thesis when I worked on an aerospace research project. So I'm really happy to join Autodesk and to communicate with you and to present some CFD interesting things to you. So let's start.
All right. So really what we did here was we snagged the same model that we got off of GrabCAD, and I'll actually, oops, let me show. This is actually what Amal and I found sitting on GrabCAD and said, well, let's take this and
so it's like the original.
Do some analyses with it.
Mm-hmm.
I think the only thing that we had really agreed upon ahead of time was what the flow rate was going to be.
Yeah, and we agreed on a 500.
So from there.
And we're going to just concentrate on simulating the flow only.
Right. Yeah, we weren't going all the way into heat transfer.
Yeah.
That was all that we agreed on. So now I don't know what's going on. This is your part of the show.
Yeah. Normally we actually thought that when you open the model, I just noticed that you didn't change the outlet. Is that right? Because normally we agree that it's a sloppy and not very efficient outlet of the heat exchanger.
That is valid. I was lazy.
How do you explain this?
Yeah, I left it as is. Your model's a little bit better, but we'll.
Yeah. So it's okay.
Mine was less clicks.
Right. So for the first model, it's the full model. It's the let's say the not clean model, where you can see in the channels you can find some openings. I think they are called fins in this heat exchanger. Yeah, and they are like rectangular. Openings, yeah, super small. We have like here 12 channels, and for each channel there is 21 small tube. Then what I've done is I modify the outlet so it looks like here on the left side, where I also extended the outlet and the inlet. So I got in the inlet a fully developed flow, and then I extended the outlet so I avoid any recirculation when measuring pressure drop or velocity there. So the approach I adopted is to take only one large channel and to delete these small tubes. So,
nice. Did I skip ahead of you?
Did you skip something? No, I think you didn't skip. Okay. So to start, I said, okay, for the full model, I have two materials so far. So I have the air, which is inside the tubes, that circulates inside the heat exchanger, and the solid material, which can be for some heat exchangers, aluminum or steel. And for my approach, I said, okay, I'm going to delete these small tubes inside the channel and to represent them or model them in another way. So I said, I had a question, okay, and how do I model this in CFD? How do I model a porous medium in CFD? So I got the idea of defining this as a resistance material. So maybe you're asking how to define it exactly according to this geometry. I noticed that, Todd, can you go to the previous slide?
Oh, did I cheat? Sorry.
Yeah.
I was ahead of you.
So for the
explaining the picture, I gotcha.
Yeah, exactly. So for the fins here, they are they have simple geometry. So we can in here calculate these the area of these openings. We can calculate the area of one opening and then multiply it by 21, the number of this opening, and then calculate the area, the free area ratio. So the next slide. Cool. So I calculated the area of the openings and divided by the total area of the large channel, and for the loss coefficient, I choose as a variation method the free area ratio. So I got this value 0.677 as a result of this equation. You can see here that it's a customized material. Under the material name, I chose my materials and then the type resistance, and then type on edit under material, and then get to rename my new material as a resistance channel, and then give the value of the free area ratio, which means the through flow K. And for the conductivity, I just chose the conductivity of air because it doesn't matter for right now, because we're not going to study the heat transfer.
Yep.
Mm-hmm. Okay, I'm gonna show a model that, yeah.
And throw the ball to Amal.
Okay, show my. Okay. Here we go. Can you see my screen?
There it is. Yes.
Okay, so this is the model I cleaned up, and here you can see there's no more tubes inside it. And this is the original model. And here's my new model. Maybe you wonder why I created such caps in here, because in CFD, when you define a resistance material without having these air caps, you will get an error saying that there is no neighboring fluid there. That means that if you define only resistance, CFD will not know if or which fluid it's gonna go through this resistance. So that's why I defined here an air cap, a cap on the inlet and on the outlet. And the first step I made, it's like modeling the whole channel, and then I said, okay, I'm gonna come here and make offset plane. So I created a plane here, just cut the surfaces, and then I said, okay, so I created this model, and I'm gonna send it to CFD to model it, and then I got an error. Can you, Todd, go to the slide, please?
Back to the slide.
Yeah. I'm gonna show the error I got.
And mine should be coming back up.
Perfect. So I went to, I got previously the simple model with only air. That means without these 2 or 3 cat parts. And then I made an update under my design and said, okay, can you import the model that I have created? And then I defined the air caps in here on the openings, inlet and outlet, and then I still have the middle part. I then edit the materials. I said edit materials, and then chose resistance, and then got the same error message. I was like, why? I've just created 2 air caps. It should work. Why you're saying that you don't have neighboring fluids? And then when I investigated my air caps, I just recognized that I should have made an extrusion, not create a plane, and that's all. That means that CFD, when I import the geometry to CFD, it took only the surfaces and defined them as volume. He didn't like made automatically a volume inside.
Oh no.
Yeah. Unfortunately.
Oh man. I was trying to. I got you now. Yeah. Okay.
Yeah, I was like.
That'll cause a problem.
Yeah.
Other thing that I wanted to throw in there, just since we're, because there's the neighboring fluid error, and just to give a little bit more background to it, that's because we're trying to calculate what the pressure drop should be, and when you're doing, basically this will boil down to a K value, and to figure out that pressure drop, you've got 1/2 rho v squared, so you need to grab the fluid density to calculate what the pressure drop is going to be, and then the software is looking to calculate it from nodes that are outside of the resistance material. The other thing that you gain by adding those caps, you want to have them just far enough that your boundary condition isn't touching volume that's doing math for you.
Yeah, right. Absolutely.
So, going a little bit deeper there. Sorry.
It's okay. It's really good to give some more details about
why that's done, because that's a common thing that happens all over the place. Fans and anything else, you always need to have that cap, and really you don't need to have a huge cap. You just need to make sure that you're going to have a node that isn't going to have a boundary condition on it when we go to calculate, because you don't want to have your zero pressure lined up right next to your resistance. Although if that's going to be, the zero pressure isn't as bad as if you've got flow rate or something like that, where it's just going to cause pressure to go a little bit nuts right on the inlet of a resistance. Food for thought.
Yeah.
Go across more than heat exchangers.
Yeah. So, next slide, please.
Yeah. There it goes.
So then, after defining my materials, I said, okay, it's time for, after defining also the boundary conditions, which is we defined the inlet, the mass flow. As we already mentioned, it's 504 kilogram per hour. And then for the whole model, but for this large channel, It's divided by 12, so that means it's 42 kilogram per hour. So, and at the outlet, I defined a pressure, a static pressure of 0. So then I moved to the meshing, and I was asking myself, should I mesh my model for the single channel? It's really important to make sure that in the narrow tubes, that means in general, or in my narrow channel, I have to mesh or to get more than 3 fluid elements between the walls of the channel. And regarding the full model, as we're gonna get like some recirculation and velocity gradient at the inlet and sometimes at the outlets of the heat exchanger. That means at the level of the tanks. So we should make sure to refine these regions. Next slide.
Yep.
No?
It's not going. There it goes. Let me see.
Cool. So during meshing, I got some like errors or bad practices that I wanted to share with you. Like, for example, here I got coerce mesh. We mentioned already in previous webinars talking about how meshing is very important to get the results. How
so sad.
I think Todd, I think it's a webinar with Royce or
I
with
think I've done one
John.
with Royce and
Yeah.
one with John,
Yeah.
talking about different meshing things, and I mean, really,
Yeah.
just to give the brief overview here, you want to make sure that you have a few nodes that aren't in the enhancement layers to be doing the calculations to have a good velocity.
Yeah, exactly.
Calculation.
Yeah, we can see here also the difference how on the refined mesh the flow is well captured, not like on the coerced mesh where we can get really wrong results if we calculate the velocity or pressure there. So we have to make sure to optimize our mesh so in a way that it captures the high gradients of pressure, velocity, and to have less runtime. Actually, we have already like a page. I can share it. I can share the link with you where you can make a mesh convergence study on how to optimize your mesh, to refine it in a way that you get not long runtime simulation. So,
do you want me to kick it over to you, or okay?
we can we can share it. Okay.
Kick it over to you. While you're grabbing that and sharing, we did get a question about how you would do the conductivity normally for when you've got a resistance and you're trying to do heat transfer. Typically, what I'll do for a starter is I'll do that weighted average of how much is fluid, how much is solid, kind of the reverse of a free area ratio, and then do the weighted conductivity between the fluid and the solid. But it's actually going to be something that you're probably going to end up having to weight a little bit higher of a conductivity, so if you think about it, because your fluid is moving, you're only going to be able to get the conduction at the near wall unless you're moving very slow. I guess it's a very velocity dependent, because you want to be able to get that heat to transfer all the way to the wall, and then it also affects what do you got? uh, what am I trying to say? Just to get the heat to transfer the way it would with conduction, because there isn't a solid there, you end up having to artificially bump up that heat transfer, and it's good to start with like a simple test model. We used to do it a lot for characterizing heat sinks, where we'd do a little flow path over a heat sink and put a block that's a resistance. It's easy to get what the resistance is for the air going through the heat sink, and then trying to characterize what that conduction is going to be so that we could get a heat load and have the same temperature profile.
Right.
That's typically how we used to do that. But a good place to start is definitely with that weighted average of an effective conductivity.
Yeah. Cool. Thanks, Todd. So, and I'm not sure if you see my
I got it. Yep.
Yeah. So it's a page under Autodesk University workshop, fundamentals of simulation CFD meshing for AEC. So in there you will find like a paragraph or a part where you see or you go through the workflow, how you can get your mesh refined, having less runtime. You can see in here how it describes the different steps that you have to go through in order to get a mesh-independent solution for your simulation. And you can find some examples of how refining the mesh, the ideal refinement of the mesh, how it leads to good results with not a long
right.
Yeah.
You've got a huge runtime when you've got that massive mesh. And what did you buy yourself? An extra 2% on the results?
Yeah.
It's not worth it in my book.
It's not, but. Yeah. Exactly.
Yeah.
So, let's move to
the next slide. So I gotta show two. And we'll go to this guy.
Cool. So it was when meshing the full model. That means the one I simplified, but I was like, oh.
All of the flow channels?
Yeah, it's all the flow channels, but without these small tubes inside. And I say, oh my God, I didn't simulate the small tubes. It's only the large channels. And I got 124 million elements. I was like, I just meshed using the automatic meshing, and then launched the simulation without even checking how many elements do I have, just launching the simulation. And then I just go out and said, okay, my simulation is running. I'm going to come back later to see the results. And then coming back later, I noticed this error message. It's saying that
the cloud solvers have 128 gig of RAM, and you broke that.
Yeah, that was crazy, really crazy. I was like, okay, I'm really wrong. You're right. We should fix this one. And then I said, okay, I think it's better to have a manual mesh in order to have like to manipulate or to make sure that I got less element than this. And now the full model, that means the simplified I run, it has only 4 million. In comparison to this, it's nothing. So I was able to run it finally. But every time you have to make sure that if you get like such a message, you have to make sure that you don't have a huge number of elements.
Right. So you can definitely, CFD is hungry for resources. That is.
Yeah. Sure. Yeah. Exactly. Especially here, we can also mention it. For example, when I was meshing, I noticed that the mesh over my channels is not really good which can affect my results. It can lead to wrong results. So I noticed that here in the corners of the channels, there is like bad wall layers. It's not going smooth over the walls. I even tried to refine the mesh as much as I can, but still get these bad corners. And then I discussed it with Todd. We suggested that we turn the blending, the wall layer blending on in order to make sure that the mesher smooth these layers on the corners and overall the model. And how did
ran out of memory again.
We were like waiting for 1 hour, and
yeah,
it's
something like that. Just bail on it.
Yeah, and I ran it locally on my computer, and I wasn't able to do anything else. Just watching this task manager, my CFD, to see how it behaves. You can see here the physical memory, it's 99%. He just
at that point it's going to take over your page file, and then yeah, it slows down. Usually, if that happens while you're solving, it'll cause the solver to exit.
Yeah, right. So I'm honestly still looking into this issue in order to find a solution for it. Still looking for something to avoid this bad corners.
We were both on vacation last week, so some of the things that we had eventually hoped for didn't get done, but that's all right.
Yeah, right.
So let's talk about some of what you found when you did get things running. Yeah.
So this is my model. It's the simple channel. I run it and then got this at the inlet of my channel. You can see here that the fluid is not fully developed at the inlet. So you can see at the beginning, it's the velocity is less than going through the channel. So in this case, if you have like this, you have always to make sure that you have a fully developed flow at the inlet, because otherwise you will get wrong results when you want to calculate any of the study variables, any of the variables you're studying. It's going to be wrong because you're not getting the good results. So.
Right. Basically, that's because you've got a uniform velocity, even when you're using a flow rate. Really what the software does is it calculates it down to, we know what the surface area is and apply the velocity there, because your velocity times your surface area is the flow rate. It just calculates it down, puts that in, but when you've got that velocity being pushed in near the corners, you're already going to be in the enhancement layer, so it's going to cause a heavy shearing right at the inlet. So you'll see a pretty heavy pressure drop, and that's kind of what you can see from that picture that Amal shows.
Yeah, exactly.
And squeezes the flow in, it's got a heavy shear.
Exactly, and this is what I got also for my inlet for the full model. I got like this velocity profile. So that's why, for that reason, as I mentioned at the beginning, I extended my inlet. So this is in this case. So the two solutions to get rid of this is either extend the inlet or define a volume flow rate and check the fully developed option. And this is the results I get for 1 hour, and then they disappeared. It was by mistake.
Mine too.
Yeah, I really wanted to show a live demonstration of the model, but unfortunately I lost the results because I calculated on another machine. So as you can see here, that that's the flow that goes into the heat exchanger or our channels. It is not uniform. You can see for some channels there is more flows that go in than other channels. So where it's really a problem in this case is for the heat transfer, because to have a high thermal efficiency inside the channels of the heat exchanger, you have to get more uniform inflow. So in this case, I would suggest that we can change the geometry of the inlet tank so that we change the location of the inlet, so to make it from the side of the tank, not really in front of it, so to get the flow goes more smoothly than this, because in this way it hits the walls and then goes inside the channels. Yeah.
That's a very interesting look too, because you can see how much we're bouncing off that back wall and pushing in.
Yeah, and then creating this recirculation, and that makes the flow doesn't go directly inside the channels.
Yep, that'll sit there and heat up. Cool stuff.
Exactly. Mm-hmm.
Oh, it's Todd's turn. Versus beauty. Here we go.
So the title was Old School. Am I the old school or you?
I am the old school. I've been long. All right. So, I took it as, really the way that I wanted to look at the model. A little bit lazy about my inlet. I just left the CAD and extended my inlets and outlets. I extended mine further than yours.
Cool.
But I wanted to look at it, and Amal did something smart with the free area ratio that I didn't do. But I was concerned when we get to this full model, we're going to have meshing problems, which Amal found out as she was running through it. I just knew that ahead of time, so I wanted to break it down to the smallest piece. I want to have results that I can move forward with. Start simple, and then have something to show, have some piece of knowledge, so that in 2 days, when my manager says, well, what are you doing? It may not look that impressive, but I can say a bunch of stuff and show pretty pictures. So I said, let's go get the pressure drop through one of the smallest channels, and then I can take that and calculate what it's going to be essentially through all of them and apply that. So with my starting simple, I also get to figure out what the mesh is going to look like. I meshed the model with just using a uniform mesh so that I'd be able to get a decent result. And it was over 1 million elements when I just took my first stab at it, and that wasn't even a converged, mesh-independent analysis. So then I kicked it over to try and get a similar answer using extruded mesh. And I don't know if we ever talked too much about extruded mesh, so I thought this would be an interesting time to bring it up. What this does is it just does it makes the whole volume into being prism elements. So you have your triangle that's being extruded down the length, and it grows so that down here, my elements are much longer in the extruded, and we have them pretty tight in the beginning. I probably could have done some more tweaks, and I was playing with this before the webinar to see if I could get it a little bit further. But essentially what I did was I calculated the K value from the pressure drop, because again it's that 1/2 rho v squared times K is going to be your pressure drop. I got my pressure drop from my one-channel analysis, and then I said, well, I can use that. And so here Amal and I are looking at pretty close to the same analysis, where we were looking for, I'm going to get some more results and be able to show a little bit more. And then
Whoa.
I ran into
This is not good.
So
this is my enemy.
right. So the software crashes while I was trying to look at results. Now I can no longer open CFD. Pop quiz. I know you saw this slide before, Amal, but you probably didn't know the pop quiz was for you. How do I get around this guy? Uh-oh, put her on the spot. Are you there?
Yep.
Do you know what to do
Okay.
here?
So I can say that it's probably a RAM problem because maybe you're running or you're having so many models and big meshes, so that CFD is like usual eating from your physical memory, so you're not able to visualize the new results. And
yeah, this one, this was a little bit worse. This was the software crashed while I was playing with the results, and it's because I was bouncing around too much and I was playing with big models. But then now I couldn't open the interface at all anymore. This has happened to me 3 times, so I was curious if it's happened to anybody else.
so it was even when you reopen it again.
No, blank UI, no model. Can't do that. CFD is dead to me. So what I had to do was go and rerun CFD config that's found in the installation directory just to get up and running again and be able to open my analysis. But once I, yeah.
And did it work?
It sounds like Casey had the same problem that I have. And yeah, those do go to development, and that's how they're going through and looking at what's going on with the error, and they're trying to put all of these things into the service packs. I don't know what causes that one specifically, but it has happened to me a few times. So I thought I'd throw that out there because I think it's due to all the changes that we've done with the UI for 2017.
Mm-hmm.
But definitely thought it was worth mentioning since I did it again in the middle of this project. So I know we're coming close to when I'd like to pass things over for questions, but we haven't seen too much coming in. So I will keep rolling with my results. Mine weren't quite as definitive as Amal's. And this was using the extruded mesh.
Okay, so it's the extruded mesh and over the whole model, or?
Well, over each one of these passages, I have the extruded mesh, I believe. So that's how I avoided what you ran into. And you ready for showing something cool here? I think this is the one. So check this out. I just meshed this right webinar. So I didn't do too much. I auto-sized it, and you can see that I was lazy. The geometry definitely still has some weird things on it that's causing, this mesh is way too tight for just a simple channel. Amal did the right thing of clean it up, but I didn't. I was lazy. But I still got to 1.5 million elements, and I have all of the channels.
Yeah, that's still good. Because I, with the simplified model, I got 124 million. This is crazy.
Orders of magnitude. Oh yeah, old school meshing controls. Let's see what the channels looked like here, because I really didn't look at it. Oh, it's terrible. Yeah, that'll happen.
Element, you didn't respect the rule.
Well, I was trying another trick, but
Yeah, well
That
done.
doesn't mean that I didn't actually run the thing and get results with a decent mesh on the full thing. So it is accomplishable.
Mm-hmm. A bit
But you need to
slowly.
make sure that you're being strategic and being smart about how we do it. Um, I just saw that Royce threw in a comment. Yeah, it's if you're getting a bunch of CER reports seemingly doing the same thing, it is a good idea to reach out to us in support just to let us know, and we can actually look up the CER number for you
Mm-hmm.
and make sure that somebody's doing something with it. Like make sure that an item is around it, especially if it's something that's a repeatable. Like every time, I don't know, in 2016 we had a lot of crash error reports when we were dealing with particle traces because we had redone how those got done.
Yeah.
Um, so when we started to get models that we could recreate it every time we made a particle trace, or maybe it was something, I don't know. I had a couple of them where it was like a summary image done in a certain way with a certain model would cause it to crash. Um, but yeah, if we have those things and can hand them over to development, then it makes it a lot easier to fix. Thanks for answering that, Royce. But I felt like that one should probably be told to everybody. Um, one of the things I didn't do was set the part. I wanted to try and look at these results, but I did want to at least make sure that I got across the point of the way that I would attack these problems, because this really only took me a few days to go from that super small channel to I can do the whole thing. And usually our first reaction is to go at that big analysis right off the bat. And it makes a lot more sense to stop and have results in a couple of hours with a simple analysis and make sure that we understand more moving forward than having that full geometry. And
Yeah.
you can start to
Takes
spot
time.
things, I noticed that I was using 1,000,000 elements, and there's 252 of these channels. 252
Mm.
million elements, that ain't going to cut it. Amal tried.
And I
But
failed.
yeah. I just knew ahead of time that that's going to happen to me, so I avoided it. But yeah, that's one of those I know to be careful about it. Um, I can't see too much here, and I can even see some wavering where this is still not mesh independent, but I've got some decent results, and I can see where that back side that Amal was seeing, these are all a lot higher velocities than I have in some of these middle channels. So yeah, making that inlet would definitely be, or changing the inlet would probably be a good design change. We didn't roll all the way into that. I don't know, maybe another webinar, but
Yeah,
I, I
I
thought
find
this
it
was
interesting.
at least
Um,
an interesting way to go.
Todd, maybe some attendees have questions like, for such a model, which turbulence model would you use? Uh, what is better to use, either for simulating only the flow or also with the heat transfer? Because I got a lot of customers asking about what is the best turbulence model to choose in this case.
So when I'm doing an internal flow only,
Mm-hmm.
I'll usually use K epsilon.
Yeah, it's like me.
Yeah, you know, if we're really trying to figure out, and it really depends on your flow type and things like that, my personal view on things is I want it to be as repeatable and easy as possible. The one thing that I did change out of the solver parameters, I used ADV5 because I wanted to be better about the pressure drop, realizing that that's probably a design constraint. You know, if you can make the pressure drop lower, which, I mean, most of that's all going to depend on the flow through the channels anyway. So if you're changing those channels, you'll get a better pressure drop, a higher flow rate, all of that stuff. Right. But here, looking at it, that if we wanted to even out our flow rate so that we have the most efficient heat transfer, I wanted to have a decent pressure drop across it, which ADV5 is going to do a little bit better for us numerically.
Yeah.
And then using the standard K epsilon, because I don't expect to have a lot of, you know, we're not looking at vortex shedding or anything like that. Once we get into those flow channels, it's a lot of straight flows. But yeah, does anybody have any questions? I haven't seen too much popping in.
You can just ask
everything
in your mind.
Or we could give everybody back a few minutes of their day. So yeah, we've gotten towards the end, and I do hope hope everybody learned something here with us today.
Yeah, thanks, Todd and Amal. That was great. I enjoyed that. There was a question earlier, though, about someone looking for the links to the box folder. So might just want to leave it there.
No, that's not up to date. It'll be so it'll be 24, I believe.
Was it on the first slide?
Yes. And isn't it? Well, and I can hold on. Let's just kill that guy.
I was talking to Ryan in the background during the presentation. These types of models are some of the hardest ones to solve in general with accuracy. So it's interesting you guys picked this one.
Oh, yeah. Yeah. Well, Amal has the automotive background, so I let her choose for how she wants to.
Yeah, because actually I was working on project to develop intercoolers for airs that should be cooled before going inside the combustion chamber of the automotive engine. But it's more complicated because we have a flow that goes out from the turbocharger and get into our intercooler. So it's like we're having a flow that have big swirls, so more challenges in there. Not only like a simple inlet, extended inlet.
Yeah, and going through the tips and tricks as we try and tackle a reasonably complicated. It's funny because you look at it and it looks simple.
Yeah,
but,
right.
Yeah, it's not going to be easy. I knew there were going to be some problems running down, so it's like, sure,
Yeah.
Let's go for it.
It's like me at first when we grabbed the model, I was like, okay, this is really simple. I can run it in one day, and then got so many questions, so many errors. Okay. Let's do it slowly.
Right. Yeah, it really does drive in that, you know, I preach that start simple, and I also like the, you know, the less changes that I have to make so that it's repeatable. You know, if I need to be using the SST turbulence models, I will, but when it's not going to give me something massive and I know I'm going to have to go through 60 clicks in meshing just to get an appropriate mesh for something. If I can get in there and K epsilon and get some reasonable results easier. If I'm going to be paying a few percent, not a big deal. If it's going to cost me 20 or 30% in accuracy, then yeah, I'm going to have to kick in there and be more careful about these analyses. But this one's hard enough with without having to remember to those clicks. You're going to be playing with all of the mesh densities and trying to come up with a good meshing strategy.
Yeah, absolutely. Cool.
So yeah, I do want to thank everybody for coming and hanging out with us, and I'm glad we've gotten these back up and running.
Thank you very much, everyone. And if you have more questions, just reach out.
Yep.
Thank you.
Thanks, everybody.